In this presentation, we're going to talk a bit about stacks. A stack is a type of memory, but it differs from RAM. Random access memory allows one to access any part of the memory provided that you supply an address. That's what we mean by random access. Any address can be chosen at random and we will go there. A stack is going to be a subsection of memory that's going to have stricter accessing rules. We'll talk about them as they arise. But those stricter rules are going to lend themselves to certain scenarios, so it's worthwhile to section off a part of the memory and call it the stack. And one thing we're going to look at is certain types of calculations that are easily performed on the stack. So if we want to write a program that performs a calculation, then we've got to talk about a calculation instruction. An instruction in general has an operator or some action, and then it has an operand or some data portion. And so when we're thinking of calculations, we often think of the operator as being binary, that there two pieces of data are required. For example, addition, 3 plus 4. So the operator is addition, that's the action, and then there are two pieces of data. And that's the level we're going to talk about it. But we know that it's possible that we might go to an even lower level where the actual instruction might take one piece of data at a time and break addition down into two instructions. One will be to load the first number, and then the second instruction of add will add the second number to it. But we're going to work at this binary operator level, and so we're going to think of our instructions as having an action and two pieces of data, two operands, or so we might call it also, instead of just operator or operation, another term is opcode, the code for the operation. So once we've determined that, then there's still yet another decision. And when we are organizing the instruction, which is going to have two data parts and an action part, we can order the operation in various ways. So we can do what's called postfix, and so then there's the two pieces of data come first and then the action. We can do what's called prefix, which is the action, then the two pieces of data. And then there's infix, which is ordered by a piece of data and then the action and then the second piece of data. Of these various orderings of the opcode and operands, we know that postfix is the one that is best suited for hardware. When we built the adder, we needed to present to it the two numbers to be added, and then they could be added. So that is the order needed by the hardware. And then we'll find that postfix is, for larger scale calculations, is particularly well suited for computers that implement a stack. That's what we'll talk about next. If we're going to do anything other than the simplest calculation of just 3 plus 4, for instance, then we need to talk about precedence, or the order of operations. So we're going to have a calculation with multiple operations of different types, and then we must discuss which operations need to be performed first. What is the order of the operations? And so an operation that must be performed before another one is said to have precedence over it. So in our example seen here of it, which is an infix example, mind you, of 1 plus 2 times 3 minus 4, the multiplication operation has a higher precedence, and that must be performed before then any of the additions. So 1 plus 2 times 3 minus 4, perform the multiplication, 1 plus 6 minus 4, then perform the addition of 1 plus 6 to get 7, subtract 4, and then get 3. So let's start off telling you what a stack is by telling you what a stack is not. So a stack is not RAM. RAM is a set of registers, and they have a sort of a spatial order or a numerical order to them. After all, they are addressable, so each register has an address, so we think of them as an order. But the order in which we access them in time has no relation to either the past order in which things have been written, or the spatial order of the registers. And that's what we mean by random access, this ability to read and write at different locations and jump all around the memory. A stack, on the other hand, is a data structure that holds the sequence of data, so in that sense it's the same as RAM, but it limits the way in which the data is accessed. This is how it's different. So the accessing order or the timing of the stack is what's different. So the stack is going to obey what's called the last in, first out, or LIFO protocol. So we will still have reading and writing, and the writing will be known as a push, and the read will be known as a pop. And as the name I hope suggests, pop is we're going to pop it off the stack. So once we read an item, then we are done with it. It is removed from the stack. So again, LIFO means that they are put on, the items are put on the stack in some order, and then when we are taking them off, when we are reading them, we must use this LIFO protocol. So we're only given access to the last one. So what we read, the first out, is the last one we put in. LIFO protocol. This stack can be implemented in hardware or software. So here's just a diagram of a stack. First, a 1 was pushed onto the stack. Then a 2 was pushed onto the stack, so the 2 is on top of the 1. Then we come by and we pop off the 2. It was on the top of the stack, so that's the one we have access to. Then we've pushed a 3 onto the stack, and then we've pushed a 4 onto the stack. So again, our only actions are pushing and popping. Pushing puts something on top of the stack. Popping takes it off of the top of the stack. Now, the top of the stack is controlled by what we call a stack pointer. So when we pushed a 1, then the stack pointer, the 1 was written in a register, and then the stack pointer was pointing at the next available register. And then when the 2 was pushed, it was written in that register that was being pointed to, and the stack pointer moves on to the next higher register. Then when we pop, when we read the 2 and use it, now the stack pointer is pointing to the 2, or we might think of it as where the 2 used to be. The 2 may still be there, but it doesn't matter because it's not something that we can read, and our next push is going to be in that location. So when we push the 3, it overwrites the 2. So it didn't matter whether the 2 was still there in memory or not, because if we read, we would read the 1, and if we push, we're right over that 2. So this is how the stack is controlled by the stack pointer. So now we have a multi-step postfix expression, and then we are going to show how to use the stack to evaluate it. So when we have a multi-step calculation, then we have the notion of precedence or order of operations. So there are things that need to happen first and things that will happen later. And the stack is going to be helpful to execute this, and that it is going to, a number can be put on the stack and sort of held onto the stack and not at the top of the stack. And then only when we're ready to do a calculation with that number will it reach the top of the stack and be accessible and then participate in the calculation. So this is going to be how the stack is going to allow us to respect our order of operations. Now, we're not going to say how this postfix expression was arrived at. We're just going to show how the stack is used to evaluate it. And so we're going to step through this calculation as a stack calculation using a website that no longer exists, unfortunately, but there are equivalent ones out there. So our basic rule is we're going to step through the postfix expression, and when we come across a number, we are going to push it onto the stack, and when we come across an operation, then we're going to take the top two numbers off the stack, perform the operation, and put the answer onto the stack. So what we first encounter is a 1, and so the 1 is pushed onto the stack. Next we encounter 2, it's a piece of data, and the 2 will next be pushed onto the stack. And here's the result of the 2 being placed on the stack, so it is accessible, being on the top of the stack. The 1 is not accessible, and we're ready to move on to the next part of the expression. We see that the next part of the expression is a 3 and number, and so it is going to be placed on the stack. Now we see the result of the 3 being placed on the stack, so the 3 is on the top of the stack, and we're ready to move on to the next character in our expression. So the next character we encounter in our expression is a plus. It is an action it is a binary operator, and so we are going to take two pieces of data from the stack, the top of the stack, so first the 3 and then the 2, and then we will perform this action on them, addition, and so add 3 and 2 and get 5, and the 5 will be placed on the stack. So here's the result. The 3 and the 2 were popped off the stack, so they are no longer on the stack, but their sum, 5, was then pushed on the stack. So at this state, the stack is a 5 at the top and a 1 underneath. Our next character in the expression is a 4. It is a number, and so the number will just be pushed onto the stack. So the 4 will be on the top of the stack. There is the result of the 4 being pushed on the stack. It is at the top, and then we are ready to move on to the next character. The next character is an asterisk or star for multiplication. And so it tells us to pop off the top two pieces of data on the stack, so the 4 and the 5, to perform the operation. So 4 times 5 giving us 20, and we will put that answer of 20 onto the stack. Here is the result of the multiplication, the 20 pushed onto the top of the stack. Now we have moved on to the plus operator. It is an action, so we are going to take off the top two pieces of data, the 20 and the 1. We're going to perform this action of addition, get 21, and put that answer, push that answer onto the stack. And here is the result, the 21 at the top of the stack, and it's the only number on the stack at this stage. Our next character is 5, a piece of data. It will be pushed onto the stack. There's the 5 pushed onto the stack, and we're ready to move on. Our next character in the expression is a 6, a piece of data. It will be pushed onto the stack. Here's the result of the 6 being pushed onto the stack, and we're ready to move on. Our next character in the expression is plus, an operation. So we're going to pop off the 6, and then pop off the 5, perform the action of addition, get 11, and then we're going to push the answer of 11 onto the stack. We see here the result of the 11 pushed onto the stack, and we're ready to move on. We next encounter a 7, a piece of data. The 7 will be pushed onto the top of the stack. The 7 has now been pushed onto the top of the stack, and we're ready to move on. The next character we encounter is an 8. 8 is a piece of data, as a piece of data is going to be pushed onto the top of the stack. There's the 8 now at the top of the stack, and we're ready to move on. Our next character is a plus, an operation, an action, and so we're going to pop off the two pieces of data, pop off the 8, then pop off the 7, perform the operation of addition. 8 plus 7 will be 15, and we're going to take that answer 15 and push it onto the stack. Here's the result with the 15 at the top of the stack, and we're ready to move on. The next character we encounter is a 9, a piece of data, and so it will be pushed onto the top of the stack. We see the 9 now pushed onto the top of the stack, and we're ready to move on. The next character we encounter in our expression is an asterisk, and so that is an action, and so we're going to pop off two pieces of data, first the 9 and then the 15, and perform the action of multiplication. 9 times 15 is 135, and we're going to push the 135 onto the stack. We see here the result with the 135 pushed onto the stack, and we're ready to move on. The next character we encounter in our expression is a star, and so it is an action. So we are going to pop off two pieces of data. We'll pop off the 135, pop off the 11, perform the action of multiplication. 135 times 11 is 1485, and we're going to push that onto the top of the stack. We see now the result of the 1485 pushed on the top of the stack, and we're ready to move on. The final character we encounter in our expression is a plus. It's an operation, so we're going to pop off two pieces of data, the 1485 and then the 21. We're going to perform the action of addition and get 1506, and then push that onto the top of the stack. And we see here the result, the 1506 pushed onto the stack. I'm just showing here some of the references used to put this presentation together.